In 1963, astronomers encountered a cosmic mystery that would forever transform our understanding of the universe. During their routine observations, they stumbled upon something extraordinary that defied all conventional wisdom of the time. What initially appeared to be ordinary stars revealed themselves to be something far more remarkable and powerful. These mysterious objects were emitting energy equivalent to trillions of suns, a scale of power that was simply unprecedented in astronomical observations. What made this discovery even more astonishing was the immense distances involved. These objects were so incredibly far away that their light had been traveling through space for billions of years before reaching our telescopes on Earth. This meant that astronomers weren't just looking at powerful cosmic objects. They were looking back in time, observing these brilliant beacons as they existed in the very early universe. These objects would come to be known as quasars, and they stand as the brightest known objects in the primitive universe. The sheer scale of a quasar's power output challenges our imagination. Consider this: a single quasar can outshine more than 100 entire galaxies combined. To put this in perspective, each galaxy contains hundreds of billions of stars, yet a quasar's brilliance surpasses all of them together. This incredible luminosity comes from a space no larger than our solar system, making quasars some of the most efficient energy-producing mechanisms we've ever discovered in the cosmos. These celestial powerhouses serve as cosmic time machines, offering us an unprecedented window into the universe's past. When we observe quasars, we're seeing the universe as it existed when it was merely 1 billion years old, a fraction of its current age of approximately 13.8 billion years. This makes them invaluable tools for understanding how the early universe evolved and how the first large-scale structures formed in the cosmos. The discovery of quasars represents one of astronomy's most significant breakthroughs, fundamentally changing our perspective on the universe's evolution and the extreme physics that governed its early epochs. Their study continues to yield new insights into the nature of space, time, and the fundamental forces that shape our cosmos. If you're fascinated by these cosmic giants and want to explore more about the wonders of our universe, make sure to subscribe to Exploring the Universe channel. By joining our community, you'll never miss any content about the fascinating world of astronomy, from the latest discoveries to in-depth explanations of cosmic phenomena that shape our understanding of space. The story of quasars' discovery begins in the late 1950s, when radio astronomy was revolutionizing our view of the cosmos. Radio telescopes were detecting mysterious sources of intense radio waves that didn't seem to match any known celestial objects. The most puzzling aspect was that when astronomers pointed their optical telescopes at these radio sources' locations, they often found what appeared to be ordinary, faint blue stars. This misalignment between appearance and behavior would turn out to be one of the most intriguing mysteries in astronomical history. As astronomers catalogued these peculiar objects, they noticed something extraordinary. These star-like points of light had radio emissions hundreds of times more powerful than those from typical galaxies. The astronomical community was baffled. How could something that looked like a modest star produce such enormous amounts of energy? These mysterious objects were initially dubbed quasi-stellar radio sources, or quasars for short, reflecting their star-like appearance, but acknowledging their bizarre nature. Enter Maarten Schmidt, an astronomer at the Palomar Observatory, who would make the breakthrough that would crack this cosmic puzzle wide open. In 1963, while studying a particularly bright quasi-stellar object called 3C273, Schmidt made a revolutionary discovery. The spectrum of light from this object showed familiar patterns of hydrogen emission lines, but they were dramatically shifted toward the red end of the spectrum. This phenomenon, known as redshift, was already understood to indicate objects moving away from Earth, but the magnitude of this shift was unprecedented. Schmidt's calculations revealed something astounding. 3C 273 was moving away from Earth at roughly 16% of the speed of light. Using Hubble's law, which relates velocity to distance, Schmidt determined that this object must be roughly 2.5 billion light-years from Earth. This was a revelation that shook the foundations of astronomy. If an object so far away could appear as bright as a nearby star, it must be producing an almost unfathomable amount of energy. The discovery of this extreme redshift was the key that unlocked the entire quasar mystery. It meant these objects weren't small, nearby stars at all, but incredibly distant, superluminous entities. The calculations showed that a typical quasar must produce energy equivalent to hundreds of large galaxies, all coming from a region roughly the size of our solar system. This incredible energy output would later be explained by the presence of supermassive black holes at the centers of young galaxies, consuming matter at prodigious rates. This initial discovery period sparked a revolution in our understanding of the universe. Astronomers began to realize that quasars represented an important phase in galactic evolution, offering glimpses of how galaxies behaved in their youth. The extreme redshifts of these objects also provided evidence for the expanding universe model and gave astronomers new tools for studying cosmic evolution at the largest scales. The work of Schmidt and his colleagues during this period didn't just solve a mysterious puzzle. It opened up entirely new fields of astronomical research. Their discoveries led to our modern understanding of active galactic nuclei, the role of supermassive black holes in galactic evolution, and the dynamic nature of galactic cores. These findings continue to influence our understanding of the universe today, showing how one carefully analyzed observation can revolutionize our entire cosmic perspective. The initial mystery of quasars stands as a testament to the importance of technological advancement in astronomy. Without the development of radio telescopes and spectroscopic techniques, these cosmic beacons might have remained unidentified for many more years. It's a reminder that every new window we open on the universe has the potential to reveal something extraordinary and unexpected. At the heart of every quasar lies a supermassive black hole, a cosmic titan millions to billions of times more massive than our Sun. These black holes are the engines that power the entire quasar system. Unlike smaller black holes that might form from collapsed stars, these behemoths lurk at the centers of galaxies, their immense gravitational pull orchestrating a cosmic dance of matter and energy on an unimaginable scale. Think of a quasar like a cosmic whirlpool, where the supermassive black hole acts as a giant drain at the center of the galaxy. Just as water spirals down a drain, matter falling toward the black hole doesn't simply plunge straight in. Instead, it forms what astronomers call an accretion disk, a vast, flattened ring of superheated gas and dust swirling around the black hole. This disk is where the real spectacle begins. As matter in the accretion disk spirals inward, it heats up to extraordinary temperatures, reaching tens of thousands to millions of degrees. At these temperatures, the disk glows intensely across multiple wavelengths of light, from radio waves to X-rays. The friction and turbulence within the disk create such extreme conditions that the matter begins to radiate energy with an efficiency that puts even nuclear fusion to shame. In fact, the accretion process in quasars can convert matter to energy with up to 40% efficiency, far surpassing the roughly 1% efficiency of nuclear fusion in stars. But perhaps the most spectacular features of quasars are their relativistic jets. From the poles of the rotating black hole system, enormous beams of particles and energy blast outward at speeds approaching that of light. These jets can extend far beyond the host galaxy, sometimes reaching hundreds of thousands of light-years into intergalactic space. They're formed by complex interactions between the black hole's intense magnetic fields and the surrounding material, creating cosmic fountains that can influence the evolution of entire galaxy clusters. The analogy of water spiraling down a drain captures the basic motion of matter in a quasar, but the reality is far more extreme. Imagine that drain glowing with the intensity of trillions of suns, surrounded by a disk of material so hot it would vaporize any known substance instantly. The water in this cosmic drain is actually plasma, matter in such an extreme state that electrons have been stripped from their atoms, moving at significant fractions of the speed of light. The entire system operates as a perfectly choreographed cosmic machine. The supermassive black hole's gravity pulls in surrounding matter, which forms the accretion disk. As this matter spirals inward, it heats up and radiates enormous amounts of energy. Some of this material, rather than falling into the black hole, gets channeled into the relativistic jets that shoot outward along the black hole's axis of rotation. This creates a cosmic searchlight effect. If Earth happens to lie along the beam of one of these jets, we see a particularly bright type of quasar called a blazar. The structure of a quasar also includes a broader region beyond the accretion disk called the corona, where high-energy X-rays are produced. This region, combined with clouds of gas and dust at various distances from the central black hole, creates the distinctive spectral signatures that astronomers use to study quasars. Different regions produce different types of emission lines, allowing astronomers to measure properties like temperature, density, and motion throughout the quasar system. Understanding the anatomy of quasars has profound implications for our knowledge of galactic evolution. These cosmic powerhouses appear to represent a crucial phase in the life cycle of galaxies, where the central black hole actively shapes its host galaxy's development through its intense energy output and massive jets. The study of quasar anatomy continues to reveal new insights into how galaxies form and evolve, making them essential objects for understanding the history and future of our universe. The physics behind quasars' incredible brilliance represents one of the most efficient and powerful energy-generating processes ever observed in the universe. Let's dive deep into the remarkable physics that makes these cosmic beacons shine so intensely. The accretion process lies at the heart of a quasar's power-generating mechanism. When matter falls toward a supermassive black hole, it doesn't simply drop straight in. Instead, due to angular momentum conservation, it forms a rotating accretion disk. As material in this disk spirals inward, several fundamental physical processes occur simultaneously. The matter experiences intense gravitational forces, causing particles to collide with each other at tremendous speeds. These collisions, combined with magnetic field interactions and viscous forces within the disk, convert gravitational potential energy into thermal and radiative energy. What makes quasars truly remarkable is their extraordinary energy efficiency. While nuclear fusion in stars converts only about 0.7% of mass into energy, following Einstein's famous E=mc2 equation, the accretion process in quasars can achieve efficiency rates of up to 40%. This means that for every kilogram of matter falling into the black hole, nearly half a kilogram's worth of energy is released in various forms of radiation. This incredible efficiency explains how quasars can outshine entire galaxies while operating from a region no larger than our solar system. The temperatures achieved in quasar accretion disks are almost beyond comprehension. The inner regions of the disk can reach temperatures of millions of degrees Kelvin, while the outer regions still blaze at tens of thousands of degrees. These extreme temperatures cause the disk to emit radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. The highest temperatures occur in regions where matter experiences the strongest gravitational forces, just before crossing the black hole's event horizon. Relativistic velocities add another layer of complexity to quasar physics. As matter approaches the black hole, it accelerates to speeds approaching the speed of light. These relativistic velocities lead to fascinating effects predicted by Einstein's theory of special relativity, including time dilation and length contraction. The material in the inner regions of the accretion disk can reach velocities up to 30% of the speed of light, while the jets ejected from the quasar's poles can achieve speeds of up to 99.99% of light speed. The combination of these extreme physical conditions creates a cosmic particle accelerator far more powerful than anything we could build on Earth. The intense magnetic fields, coupled with the relativistic velocities and extreme temperatures, cause particles to emit synchrotron radiation, which contributes significantly to the quasar's overall luminosity. This process is particularly important in creating the radio emissions that led to the initial discovery of quasars. If you're captivated by these cosmic giants and their incredible physics, don't forget to like this video and share your thoughts in the comments below. Here's an intriguing question to consider. What do you think would happen if a quasar suddenly appeared near our Milky Way? Would its intense radiation affect life on Earth? How would it influence the dynamics of our galaxy? Leave your thoughts in the comments section and let's discuss these fascinating possibilities together. Don't forget to subscribe to Exploring the Universe for more mind-bending content about the cosmos and its most extreme phenomena. The physics behind quasars continues to challenge our understanding of the universe and pushes the boundaries of known physics. Each new observation brings fresh insights into these remarkable objects, making them an endless source of fascination for astronomers and physics enthusiasts alike. The era of quasars represents a crucial chapter in the cosmic story, taking us back to a time when the universe was in its relative youth. Let me paint a picture of this fascinating period that shaped the cosmos as we know it today. The quasar epoch primarily occurred when the universe was between 1 and 3 billion years old, marking a period of incredible cosmic activity and transformation. During this time, the universe was significantly more compact than it is today, and matter was more densely concentrated. This dense environment provided perfect conditions for the formation of the first large-scale structures and the birth of quasars. In this early universe, the first generations of stars had already lived and died, enriching their surroundings with heavier elements. As gravity drew matter together, the first galaxies began to take shape. At their centers, enormous concentrations of matter collapsed to form supermassive black holes. These early black holes, feeding voraciously on the abundant matter surrounding them, gave birth to the first quasars, lighting up the cosmic darkness with unprecedented brilliance. The role of quasars in cosmic evolution cannot be overstated. As these powerful objects blazed across the early universe, their intense radiation and powerful jets significantly influenced their surroundings. Quasars effectively acted as cosmic feedback mechanisms, their powerful outflows regulating star formation in their host galaxies. Their intense radiation could either trigger star formation by compressing gas clouds or suppress it by heating and dispersing the gas needed to form new stars. Perhaps most remarkably, quasars played a crucial role in the reionization of the universe. During this period, their intense ultraviolet radiation helped transform the neutral hydrogen that permeated space back into an ionized state, making the universe transparent to light as we see it today. This process was essential for the universe's evolution into its current state. The distribution of quasars across the observable universe tells us a fascinating story about cosmic evolution. Astronomers have discovered that quasars were much more common in the early universe than they are today. The peak of quasar activity occurred roughly 10 billion years ago, and since then, their numbers have steadily declined. This pattern suggests that quasars represent a phase in galactic evolution, a period of intense activity that most large galaxies, including our own Milky Way, likely experienced in their youth. Modern observations have revealed that quasars tend to cluster together in certain regions of space, tracing the large-scale structure of the universe. This distribution isn't random, but follows the cosmic web of matter, with quasars often appearing at the intersections of vast filaments of galaxies and dark matter. Their presence helps astronomers map the distribution of matter in the early universe and understand how cosmic structures formed and evolved. Today, we observe far fewer active quasars in the nearby universe. Most have gone dormant as their central black holes exhausted their readily available fuel supply. However, we can still see their legacy in the supermassive black holes that lurk at the centers of most large galaxies, including our own. These silent giants are essentially retired quasars, remnants of a more energetic cosmic past. The study of the quasar era continues to provide crucial insights into galaxy formation and evolution. By observing quasars at different distances, and thus different times in the past, astronomers can piece together how galaxies grew and evolved over cosmic time. This has led to our current understanding that the growth of supermassive black holes and their host galaxies is intimately linked, with each influencing the other's development throughout cosmic history. The era of quasars stands as a testament to the dynamic and evolving nature of our universe, reminding us that the cosmos we observe today is very different from its early days. Understanding this epoch helps us piece together our cosmic origins and potentially glimpse the future evolution of the universe. The diversity of quasars and their related phenomena represents one of the most fascinating aspects of these cosmic powerhouses. Let's explore the various types and variations of these remarkable objects and understand how they relate to each other in the grand cosmic scheme. Radio loud and radio quiet quasars represent the first major classification in quasar types. Radio loud quasars, which make up about 10% of all quasars, produce powerful radio emissions that can be millions of times stronger than those from radio quiet quasars. This difference is primarily attributed to the presence of large, powerful jets of particles streaming from their poles. These jets, accelerated to nearly the speed of light, interact with surrounding matter to produce intense radio emissions. In contrast, radio-quiet quasars possess either weak jets or none at all, resulting in significantly lower radio emissions despite being equally bright in optical wavelengths. Blazars represent perhaps the most extreme variation of quasars. These objects are essentially quasars whose jets are pointed almost directly at Earth. Due to this alignment, the radiation from the jet is highly focused and amplified by relativistic effects, making blazars appear extraordinarily bright and highly variable. Their brightness can change dramatically over periods as short as a few hours or days, a remarkable feat considering the enormous scales involved. This rapid variability provides astronomers with valuable insights into the physics of relativistic jets and the extreme conditions near supermassive black holes. Seyfert galaxies represent another fascinating variation in the family of active galactic nuclei. Named after Carl Seyfert, who first identified them in 1943, these are spiral galaxies with extraordinarily bright nuclei. Unlike typical quasars, Seyfert galaxies are close enough that we can observe both their bright central regions and their host galaxies. They're divided into two main types. Type 1, Seyferts show both broad and narrow emission lines in their spectra, while Type 2 Seyferts show only narrow lines. This difference is now understood to be primarily due to viewing angle rather than fundamental physical differences. The relationship between quasars and active galactic nuclei, AGN, is particularly important for understanding galactic evolution. In fact, quasars are considered the most powerful type of AGN. The current unified model of AGN suggests that quasars, Seyfert galaxies, blazars and radio galaxies are all fundamentally the same type of object, supermassive black holes actively consuming matter, but viewed from different angles and at different stages of activity. This unified model has been one of the most successful theories in modern astronomy, explaining the diverse appearances of these objects through differences in viewing angle, power output, and host galaxy properties. Within this unified framework, other variations emerge based on specific characteristics. Radio galaxies are essentially radio-loud quasars viewed from the side, where the bright central region is obscured, but the radio jets are clearly visible. BL-Lacerti objects are blazars that show very weak or no emission lines in their spectra. Optically violent variables are quasars that show rapid changes in their optical brightness. Low ionization nuclear emission line regions represent a lower power version of AGN activity. The power output of these objects forms a continuous spectrum from the most powerful quasars down to the weakest liners. This spectrum suggests an evolutionary sequence where AGN activity may represent a phase that many galaxies go through, with different types possibly representing different stages in this evolution. Modern observations have revealed even more complexity in this family of objects. Some AGN show changing characteristics over time, transitioning between different types. Others show hybrid properties that don't fit neatly into any single category. These changing look AGN provide valuable insights into how these objects evolve and the physical processes driving their behavior. Understanding these variations and their relationships has profound implications for our comprehension of galactic evolution. Each type provides different clues about the nature of supermassive black holes, the mechanics of matter accretion, and the ways in which these powerful objects influence their host galaxies. As our observational capabilities continue to improve, we may discover even more variations and subtypes, further enriching our understanding of these fascinating cosmic phenomena. The brightest known quasar is an extraordinary object called TON 618, which harbors one of the most massive black holes ever discovered. This cosmic titan contains a black hole with a mass of approximately 66 billion times that of our Sun, making it one of the most massive known objects in the universe. TON 618's luminosity is almost unimaginable. It shines with the brightness of around 140 trillion suns, making it one of the most luminous objects we've ever observed. This incredible brightness allows us to see it clearly, despite it being roughly 10.4 billion light-years away from Earth. When it comes to the most distant quasar ever observed, astronomers have detected J0313-1806, a quasar that existed when the universe was only 670 million years old, less than 5% of its current age. This ancient quasar, discovered in 2021, contains a supermassive black hole, roughly 1.6 billion times more massive than our Sun. Its extreme distance not only makes it a record holder, but also poses fascinating questions about how such massive black holes could form so early in the universe's history. The very existence of this quasar challenges our theories about how quickly supermassive black holes can grow. The connection between quasars and galaxy formation represents one of the most intriguing aspects of cosmic evolution. Quasars appear to play a crucial role in shaping their host galaxies through a process astronomers call feedback. Their powerful radiation and jets can either stimulate or suppress star formation in their host galaxies. This relationship appears to explain the observed correlation between the mass of a galaxy's central black hole and the mass of its bulge, a relationship known as the M-sigma relation. This connection suggests that the growth of supermassive black holes and their host galaxies is intimately linked, with each influencing the other's development. Quasars serve as invaluable cosmic tools for mapping the universe. Their extreme brightness makes them visible across vast distances, allowing them to act as cosmic lighthouses. As their light travels through space, it passes through clouds of gas and dust between us and the quasar. By studying how this light is absorbed and altered, astronomers can map the distribution and composition of matter along these vast cosmic distances. This has led to the creation of three-dimensional maps of the universe's large-scale structure, revealing the cosmic web, a vast network of galaxies and dark matter that forms the backbone of our universe. Some additional fascinating facts about quasars include some quasars spin at nearly 85% of the speed of light, making them some of the fastest rotating objects in the universe. The energy output of a typical quasar in 1 second equals the energy our sun will produce in millions of years. Some quasars shoot out jets of material that extend for hundreds of thousands of light years, longer than the diameter of most galaxies. A few rare quasars have been observed to turn off within human timescales, giving astronomers unprecedented opportunities to study how these objects evolve. The light from distant quasars helps astronomers test Einstein's theory of general relativity by observing how their light bends around massive objects in a process called gravitational lensing. Furthermore, quasars continue to surprise astronomers with new discoveries. Recent observations have revealed pairs of quasars in the process of merging, binary quasar systems orbiting each other, and even fossil quasars that appear to have recently shut down, leaving behind ghost-like structures in their host galaxies. Each of these discoveries provides new insights into how these cosmic behemoths form, evolve, and eventually fade away. The study of quasars also helps us understand the early universe's chemistry. By analyzing the light from distant quasars, astronomers can determine the abundance of different elements in the early universe, providing crucial information about cosmic chemical evolution and the formation of the first stars and galaxies. These cosmic curiosities continue to captivate astronomers and the public alike, serving as reminders of the incredible phenomena that exist in our universe and the fascinating insights they provide into cosmic evolution and the nature of space and time itself. When it comes to expert perspectives on quasars, we must begin with the groundbreaking insights of Maarten Schmidt, whose pioneering work in 1963 revolutionized our understanding of these cosmic objects. As Schmidt famously stated, "The discovery of quasars has shown us that the universe is far more energetic and dynamic than we ever imagined." His initial observation of 3C273 led him to conclude, "We were seeing something that simply couldn't be explained by our existing models of stellar evolution." Modern researchers continue to build upon Schmidt's foundational work. Dr. Priyamvada Natarajan, a leading expert in supermassive black holes and quasars, notes that quasars represent nature's most efficient engines, converting matter into energy with unprecedented efficiency. Recent studies have revealed increasingly complex relationships between quasars and their host galaxies, with Dr. Roger Blandford suggesting that the interplay between quasars and galaxy formation is like a cosmic dance, each partner influencing the other's movements. Current debates in the field focus on several key areas. One major point of discussion centers on how supermassive black holes could grow so quickly in the early universe. Dr. Xiaohui Fan, who has discovered many distant quasars, explains, "Finding these massive black holes so early in cosmic history forces us to rethink our theories about black hole formation and growth." The concept of dormant quasars has sparked particular interest in the astronomical community. Dr. Julie Hlavacek-Larondo suggests that most massive galaxies in our local universe likely harbor dormant quasars in their centers, including our own Milky Way. These sleeping giants could potentially reawaken if they receive a fresh supply of material, perhaps through galactic mergers or passing gas clouds. Now, for our interactive moment, Let's pause and consider a fascinating thought experiment. If we could travel to a quasar, how long would it take to reach its maximum brightness zone? Consider this: the closest known quasar is millions of light years away, and even traveling at the speed of light, we'd need to cross vast distances of space. But the real challenge isn't just the journey, it's approaching the intense radiation and gravitational forces of the quasar itself. At what point would the conditions become too extreme for any spacecraft to survive? Before you unpause, think about these points. Light from even the nearest quasar takes millions of years to reach us. The intense radiation would make approaching a quasar incredibly dangerous. The gravitational forces near the central black hole would become increasingly extreme. Time itself would begin to distort as we approach due to relativistic effects. When you're ready to learn more about this fascinating journey and its implications, unpause the video and we'll explore the answer together. Recent expert predictions about quasar evolution suggest that while most nearby quasars are now dormant, they could reactivate under the right conditions. Dr. Meg Urry points out that understanding the life cycle of quasars is crucial for understanding galaxy evolution as a whole. Indeed, this connects to ongoing research about the potential for quasar reactivation in our own galactic neighborhood, and what that might mean for future cosmic evolution. As we continue to develop more powerful telescopes and detection methods, experts predict we'll discover even more varieties of quasars and better understand their role in cosmic evolution. The upcoming generation of telescopes promises to reveal new insights into these fascinating objects, potentially revolutionizing our understanding once again, just as Schmidt's discovery did over half a century ago. The discovery of binary quasars marked a revolutionary moment in our understanding of these cosmic giants, opening new frontiers in the study of galactic evolution and gravitational waves. When astronomers first identified pairs of quasars orbiting each other, it was like finding the missing piece of a cosmic puzzle that had long eluded scientists. These celestial pairs emerged as compelling evidence for galaxy merger scenarios in the early universe. Initially spotted as unusually close pairs of bright objects, binary quasars revealed themselves to be the result of galaxies colliding and merging billions of years ago. Each quasar in these pairs represents the active supermassive black hole from its original galaxy, now locked in an orbital dance that will eventually end in their combination into an even more massive black hole. The implications of binary quasars for galactic evolution are profound. Their existence suggests that galaxy mergers were more common in the early universe than previously thought, helping explain how today's largest galaxies and most massive black holes formed. These cosmic collisions not only brought together the galaxy's stars and gas, but also their central black holes, leading to periods of intense quasar activity as the black holes consumed the surrounding material. Perhaps most excitingly, binary quasars provide a crucial link to gravitational waves. As these massive black holes spiral toward each other, they create ripples in the fabric of space-time itself. While current gravitational wave detectors are not yet sensitive enough to detect the long wavelength signals from orbiting supermassive black holes, future space-based observatories like LISA will be able to detect these cosmic ripples. This will give us a completely new way to observe and study these massive cosmic collisions. The final merger of binary quasars represents one of the most energetic events in the universe. When two supermassive black holes finally combine, they release enormous amounts of energy in the form of gravitational waves. This energy release can briefly exceed the combined light output of all the stars in the observable universe. The detection of such events will not only confirm our theories about quasar evolution, but also provide new tests of Einstein's theory of general relativity under the most extreme conditions imaginable. Recent observations have revealed even more complex systems, including triple quasars and multiple black hole systems within single galaxies. These discoveries suggest that the growth and evolution of galaxies and their central black holes is even more intricate than previously imagined. Some binary quasars have been found to be separated by distances as large as 100,000 light-years, while others are mere light-years apart, providing snapshots of different stages in the merger process. The study of binary quasars has also shed light on how supermassive black holes grow so quickly in the early universe. The merger process provides a mechanism for rapid black hole growth, helping explain the existence of extremely massive black holes when the universe was less than 1 billion years old. This understanding is crucial for our models of how the first galaxies formed and evolved. Looking ahead, astronomers anticipate that the combination of traditional observations, gravitational wave detection, and advanced computer simulations will reveal even more about these fascinating systems. The era of multi-messenger astronomy, where we can observe cosmic phenomena through both electromagnetic radiation and gravitational waves, promises to revolutionize our understanding of binary quasars and their role in cosmic evolution. The story of binary quasars continues to unfold, reminding us that even the most powerful objects in the universe rarely exist in isolation. Their discovery and ongoing study represent one of the most significant chapters in modern astronomy, connecting our understanding of galaxy formation, black hole physics, and the fundamental nature of space and time itself. The study of quasars has profoundly transformed our human understanding of the cosmos, challenging and expanding our perspective of our place in the vast cosmic tapestry. When astronomers first discovered quasars in the 1960s, they shattered our previous conception of the universe's scale and energy limits. Here were objects so powerful they could outshine entire galaxies, yet concentrated in spaces smaller than our solar system. This discovery forced us to confront the reality that the universe was capable of processes far more extreme than we had imagined. It was a humbling moment for humanity, revealing that our most powerful technological achievements were modest compared to these natural cosmic engines. The impact on modern cosmology has been equally revolutionary. Quasars serve as cosmic lighthouses, allowing us to probe the universe's earliest epochs. By studying these distant beacons, we've gained unprecedented insights into how the universe evolved from its primitive state to its current form. Their light, traveling across billions of light-years, carries information about the intervening space, helping us map the distribution of matter throughout the cosmos. This has led to the discovery of the cosmic web, a vast network of galaxies and dark matter that forms the universe's basic structure. Perhaps most remarkably, quasars have helped us understand our own cosmic mortality. Our Milky Way galaxy, like many others, harbors a supermassive black hole at its center, essentially a dormant quasar. This revelation has profound implications for our galactic future. Astronomical observations suggest that our galaxy is on a collision course with the Andromeda galaxy, set to occur in approximately 4.5 billion years. This cosmic collision could potentially reawaken our dormant black hole, transforming our galactic neighborhood into a quasar once again. The study of quasars has also revolutionized our understanding of physics itself. These objects exist in conditions so extreme that they serve as natural laboratories for testing theories of gravity, relativity, and quantum mechanics. They've helped confirm Einstein's theory of general relativity and provided insights into how space and time behave under the most extreme conditions imaginable. This knowledge has practical applications, influencing our understanding of everything from nuclear physics to the development of advanced technologies. Looking toward our cosmic future, quasars offer valuable lessons about the cyclical nature of galactic evolution. They show us that galaxies, including our own, go through periods of intense activity followed by relative quietude. This understanding helps us place our current cosmic epoch in context. We live in a relatively peaceful period of our galaxy's life, but this hasn't always been the case, and won't always remain so. The human implications of quasar research extend beyond pure science. These objects remind us of the incredible scales and energies present in the universe, helping us appreciate both our cosmic significance and insignificance. While we may be small compared to these cosmic giants, our ability to understand and study them demonstrates the remarkable capabilities of human intelligence and scientific inquiry. Quasars also teach us about the interconnectedness of cosmic systems. Just as quasars influence their host galaxies through complex feedback mechanisms, we're learning that actions on one scale can have far-reaching consequences on others. This lesson has particular relevance as we grapple with global challenges on Earth, reminding us that local actions can have system-wide effects. Furthermore, quasars demonstrate the importance of long-term thinking in understanding our cosmic environment. The processes involved in quasar formation and evolution occur over millions or billions of years, encouraging us to think beyond human timescales and consider our place in the broader cosmic story. This perspective can influence how we approach challenges on Earth, promoting consideration of long-term consequences and sustainable solutions. The future implications of quasar research continue to emerge. As we develop more powerful telescopes and detection methods, our understanding of these cosmic behemoths grows, potentially offering new insights into fundamental questions about the nature of space, time, and existence itself. This ongoing quest for knowledge exemplifies humanity's endless curiosity and determination to understand our cosmic surroundings. In essence, quasars have not only revolutionized our scientific understanding of the universe, but have also provided a cosmic perspective that influences how we view ourselves and our place in the universe. They remind us that we are part of a dynamic, evolving cosmos, one where change is constant and where the future holds possibilities both challenging and inspiring. This knowledge enriches our understanding of not just the physical universe, but also our role as conscious observers and interpreters of cosmic phenomena. Quasars stand as far more than mere brilliant beacons in the cosmic darkness. They are living witnesses to the universe's youth, narrating an epic tale of galactic formation and evolution spanning billions of years. These extraordinary objects represent nature's most powerful sustained energy sources, serving as cosmic lighthouses that illuminate our understanding of the early universe. Through their study, we've uncovered fundamental truths about the nature of space, time, and the evolution of cosmic structures. These massive engines of light and energy have shown us how galaxies grew from the cosmic web of matter in the early universe, how supermassive black holes shaped their host galaxies, and how the complex interplay between matter and energy drove cosmic evolution. The legacy of quasars continues to influence our understanding of the present-day universe. Every massive galaxy we observe, including our own Milky Way, likely harbors a dormant quasar at its center, a sleeping giant that tells of more active times in its past. These objects remind us that the universe is not static, but dynamic, constantly evolving through cycles of intense activity and relative quietude. Looking forward, quasars remain crucial to advancing our knowledge of the cosmos. As we develop more powerful telescopes and detection methods, these distant beacons will continue to reveal new insights about the universe's earliest epochs, the formation of the first galaxies, and the fundamental physics that governs our cosmos. Their study bridges our understanding from the universe's youth to its current state, helping us predict its future evolution. In essence, quasars embody the dynamic and evolving nature of our universe. They demonstrate that even the most powerful phenomena in the cosmos are part of a greater cosmic cycle, one that continues to unfold as we watch and learn. Through their brilliant light, we glimpse not just distant objects, but the very story of our cosmic origins and evolution. If you've enjoyed this journey through one of the universe's most fascinating phenomena, don't forget to subscribe to Exploring the Universe channel. Hit the notification bell to ensure you never miss any of our captivating content about the cosmos and its wonders. Please show your support by leaving a like and sharing this video with your friends who share your curiosity about the universe. Join our growing community of space enthusiasts as we continue to explore the mysteries of the cosmos together. See you in our next cosmic adventure.